Thanks again for inviting me. And as I couldn't see who was speaking right now, but as I was introduced, I am currently a faculty on Toronto, and I spend my time between Toronto, UoT, and NVIDIA. One of the core things that I've been working on is this idea of what sort of structured inductive biases do we need for reinforcement learning, particularly for decision-making in embodied systems like robots. And I'm going to give you a couple of insights into that line of work today, and also hopefully provide you a broader picture of what we have discovered to be the case due to the lack, per se, of structure in RL. So let's begin. Without wasting any time, let me directly get to the point. The point is that, well, in the last few years, we've seen applied AI in vision and language basically built on top of structured models, data, and compute. And we've seen the larger progress in each of these dimensions basically correlates very directly with performance, right? Larger data sets help, at times more compute helps, but structured models cannot be, what you would say, ruled out, right? So one could really argue that these three things are ingredients of modern machine learning algorithms. And when I use the word structured models, these are, for example, in vision, variants of convolution networks; for language, variations of attention-based models, including transformers; large data sets, of course, for both vision and language, often scraped from the web. And then all of them are trained with very large-scale compute, and of course, at times you also need very large-scale compute even to do inference. Somehow, despite robotics being very related, we have not been able to use all of these things, right? The models we use in robot learning are not very large. The data sets are definitely not very large. Many times they're not even IID. They're very specific and skill-based. And once we start thinking about this, then we're not really using large-scale compute for learning either, actually. We are constrained in a sense. And if we really go back to a lot of this debate on how should we discover this structure, or what sort of structure would we use here? You could argue one side of this sort of extreme spectrum is structured environments, structured solutions. We build structured pipelines. At times, these things can be independent processes of perception, planning, and control. And this is something that has worked and served us well. But the problem is that this is one problem in one solution kind of approach. On the contrary, you could flip it around and you can basically say just add data. Right, so we will build end-to-end models, and again, at this point, this is more of a caricature-ish example, not really how we would do it, but just scaling is not sufficient either. One could even argue that neither of these methods are kind of sufficient for the problem we are trying to do in robotics. Right, very expert-driven methods require, first of all, experts. They are very limited in applicability, and often performance versus flexibility trade-offs exist. On the contrary, using data-only approaches for discovering the structure, first of all, may have computational sustainability problems. Data itself may not be available. And then, even so, auto-distribution errors have been hard to get around. It's basically a problem of whack-a-mole. Now, it's not as if that machine learning people have not known this trade-off, right? People from philosophy, psychology, learning, even deep learning, have been arguing that inductive biases are essentially necessary for achieving generalization. And in fact, these biases are necessary for choosing one solution over other, because just a single solution may not even be viable. This problem, even with very large data set, may result in multiple optima, and you have to choose one which generalizes. So in a sense, one could argue that there is no notion of generalization without structure, definitionally. What do we mean by structure? Often this kind of structure would come up in literature with the name of domain knowledge, inductive biases, symmetries, priors. And of course, the other aspect of this puzzle is data, whether the data is coming online, offline, simulated, real, labeled, self-supervised, in the loop. While as a group, we work on both of those problems, today I'm going to focus only on the problem of, first of all, finding out that if we are lacking structure, and two, what sort of structure would be useful. So let's look into that. Let's look into, again, vision and language. There are different kinds of structure that people have looked at, right? So relational inductive biases that are independence, locality, sequentiality, attention methods, transfer learning methods, and even contrastive learning methods, which allow you to learn maybe representations that generalize. But when we think of robotics, particularly using reinforcement learning, many of you are already aware of this paradigm. We are interested in finding a functional mapping which maps from some observation to some action space, let's say, that we can use on the robot. I would argue this is a very crude picture. To find out what we are missing, we need to go slightly deeper. That said, this framework of using reinforcement learning, at least in the way that we've seen in the last, I would say, 5 to 7 years, has resulted in surprisingly remarkable efforts across the world, actually, across many of our colleagues have seen very interesting works. But often we see that these things are what you would call, or at least what I would call, slower methods in learning, and often very narrow. Each of these methods are designed for specific tasks. And what we really want is the ability to learn fast, which I would argue one of the motivations for this workshop has been, and also learning broad in a sense that how can we learn multiple tasks with a similar representation. So really the question we are asking ourselves is, what structured biases enable autonomy or generalization in autonomy, particularly for decision making? And this could be different from what we have seen in vision and language. So let's go deeper into, well, anatomy of an adult agent. The outside loop, most of us are aware of, but when we really practically do this, we get some observation and we do some sort of processing. This processing may be through a perception block, which results in some abstract state that we have. This could be just a set of features, by the way. Then this set is passed through some functional mapping, which outputs an action space. And then we have some sort of decoder or mapping, which converts that into usable control. Often when you're using reinforcement learning algorithms, we have two more models. One is ideally of some sort of dynamics model, a transition model. And depending on what algorithms we are using, we might also have a value function. And depending on how we use these models to update the agent, the orange block, we will also need some sort of update rule. This problem can indeed be solved in many ways. Let's look at one particular algorithm, which is formally known as off-policy RL. In this case, you would basically have an interaction policy, what we call pi behavior, that can be used to create data. Once you have the data, you can use some sort of update rule. Let's say the update rule is Q-learning, and you can use that update rule to update your policy, and then iterate with the new policy being the behavior policy to collect new data, and then you can control this behavior. So this is, of course, a very broad picture of what an off-policy RL algorithm may look like. Now, the first question I might ask is, well, where is this data coming from? And even if we have this data, can we use this a bit more efficiently? Why is this question of efficiency arising? Well, robot data is kind of expensive. People have attempted creating data-driven approaches in robotics for a while in different tasks. And in many of these places, we found that the data is either for very short horizon skills, data is often skill specific, data is platform dependent, and scaling to other skills is not clear how I can use the data across skills, and it's an open question. So being able to use data through some sort of augmentation or relabeling would be very cool. So we went out to sort of study the problem of augmentation in RL. this is something that has resulted in significant performance boost in a couple of domains. There are lines of work which talk about goal relabeling in off-policy RL, hindsight experience replay in particular, which basically uses data that has already been observed for a particular goal and basically says that wherever we ended up must have been the real goal. If I say that, then can I learn a policy to get to certain goals? On the contrary, folks who are working with visual input have also done a lot of relabeling in the input space. That has also resulted in substantial amount of let's say, efficiency boost in learning rates. Now, if we look at both of these problems closely to find out what is going on and then what is the unified view to explain these things, in both of those cases, it turns out that the variable we were intervening on was actually independent of dynamics. So in the case of HER, we are basically relabeling the goals, which is independent of dynamics. And then because the rendering process is independent of underlying dynamics as well, you can relabel or change the images while keeping the underlying dynamic process intact. So the common thing that evolved here was if we can figure out the causal mechanism that is underlying this process, then we can exploit independence of causal mechanisms from transition dynamics and relabel data. And we can create a lot of data which can in principle be, let's say, technically correct, and it would provide us with a unified mechanism of data augmentation. So this is where we came up with the idea of counterfactual reasoning to generate causally valid data, which can be counterfactual. And this is not just visual or goals, but it can actually be even in states that you have observed, as long as you can figure out which states depend on which ones. So just to give you a very quick overview of what this might look like, consider a very simple example of two balls on a pool table, right? There is a blue ball and an orange ball, and I give you two data points. Now, based on these two data points, I ask ourselves, is this new data point a viable data point? Well, one could argue that I can take the orange ball from scenario 1 and the blue ball from scenario 2, and because they are never interacting with each other, you could actually basically say that I can do independent compositional generalization by combining these two, and I don't need to observe this data point, but I believe this would be true. On the contrary, is this a viable data point? And one could argue that in this case, that there is a potential collision or interaction that I have not observed, and I have no evidence of what happens if the interaction happens. So these are places where the two objects or the two entities are not independent. Hence, we need evidence of possibility. Now, taking this to robotics, you can really think of this as maybe a two-arm robot, which is operating in shared workspace, but never interacting with each other. Then even if they are operating in shared workspace, but with the different timings, it should be fine. You can augment that data set. However, when they do handoffs, that is something that we don't know if it will work or not. We will need new data. Now, basically, what we're doing in this case is figuring out what the causal model underlying the data is, particularly not a global causal model, but a local causal model. When I use the word local, local is both in space and in time. If you have, let's say, a two-arm robot, you could argue that it is anything that is in left hand is independent of the right hand if the right hand is far away. And same goes also in time. Once you can do that, then you can actually augment data compositionally because of independence of sub-mechanisms in the discovered causal mechanism, right? So how do we build such causal mechanisms? In simple environments like this, let's say the ball environment, an independence of causal mechanism could actually be just learned through learning a dynamics model And if my Jacobian is indeed, let's say, block diagonal, then I could argue that the two objects or the two entities are indeed independent of each other. Of course, this was a very simple example, but this idea can be scaled by learning dynamics through transformer models, which is what we attempted in this paper. And then we used a mask, a learned mask on the dynamics model to infer causality here. Once you have this model, then you can again use this to augment data during learning in offline off-policy RL, and doing so allows you to use or extract more performance of the same data. So what we see here is basically at about half the data, we can achieve the same performance through the use of this mechanism of data augmentation. While in simple tasks, this is not very viable, but as soon as the tasks become harder, the x-axis becomes much longer, suddenly, not only is this performance gap in terms of speed, so we can reach, let's say, higher levels of performance for the same amounts of data, but also final performance or steady state performance could also be very high. In this case, in both of these tasks, a 6-axis robot arm is interacting with the block. In the first case, it's just pushing a single block. In the second case, you're pushing multiple blocks. So what I just talked about is this idea of counterfactual data can help, counterfactual data augmentation can help data efficiency in off-policy RL. This is, by the way, not the only way to improve structure. We have also studied the question of, can we learn this causal structure automatically? This was a line of work that we did where we can discover causal structures directly from visual data. This was published, I think, 2 years ago at NeurIPS, where we look at videos to discover in an unsupervised manner causal structure of, let's say, soft objects like pieces of clothing without having particular models for, let's say, a shirt or a pant or a towel. A single model would work across multiple items of clothing. This, again, as I said, is only one aspect of it. What about, let's say, if we looked at the update rule? When we do the updates here, often we assume that the architecture we use is a 2 or a 3 layer MLP. But does the choice of architecture matter? Surprisingly, we found that yes, it does. Using denser architectures like ResNets in policy or value improves sample efficiency. This was a very surprising yet simple result. The change in the algorithm is fairly low. However, the performance bump was basically across all environments where we evaluated off policy RL. Often when we use these sort of update rules, we assume Q function is, let's say, the only definition of utility function we should be using. But why? Often Q function assumes that we are solving an infinite horizon problem. In many cases, we may not be. So we also found that instead of using a Q function, using something like a cumulative accessibility function, which basically builds in time or time to go into the utility function, we can represent multimodal, multi-goal, and horizon-aware solutions. In a sense, basically saying that you can build in risk while learning the utility function or learning this value function. And you can also achieve multimodal solutions depending on how much time you're going to provide the agent. Now, this was just one way of solving RL, right? Let's go back to the bigger picture, which was structure broadly in RL. The story doesn't really stop there, right? We can also ask, if we were to use model-based methods, what sort of structured models would we use in these cases? We have found that hierarchical latent variable models induce particular kind of structure that is not possible with simple end-to-end models. And these hierarchical latent variable models can then be used for reasoning not only in continuous space, but continuous and discrete space. So an example is a robot trying to interact with multiple pieces of objects, where the continuous decision is where to push the object, but the discrete decision is which object to push because they're outside the path that is marked on the table. Similarly, when we do model predictive or model-based RL, often we use model learning objective, and the model learning objective is basically prediction. Prediction is in some sort of MLE or MSE, but is that the right thing to do always? In fact, we found that MSE may not actually be sufficient. In fact, using task-aware objective can help more efficient and targeted model learning. This is a paper at ICRA earlier this year, where we talked about that there are many cases where the input dimension of observations may have very high dimensions that modeling everything may not be useful or even viable at times. Model may not have sufficient capacity. In these cases, focusing on task-aware aspects of the state or observation can help learning much better. Right? So this was yet again only one aspect of the picture. Let's shift the focus to the input model. Can we have better structure or better learning strategies for perception? In this case, they found that you can use particular kinds of contrastive learning models to build better input representations from observations to, let's say, an abstract state, particularly in multimodal cases. And this abstract state can be learned independent of the policy and will likely generalize across multiple tasks that it was not trained for. At the same time, if you flip it on the other side, should we choose better action abstractions? Turns out, yes. We started out by looking at action abstractions with end effector spaces, basically saying that instead of predicting direct joint space torques or joint space positions, it is better often to reason or for policy to let reason in task space representations. So in this case, it can be operational space representations or even better, variable impedance control, which is allowing the system or the policy to decide what phase of the task the system is in so that it can be adaptively compliant as the task progresses. What it allows us to do is not only more efficient training of reinforcement learning policies directly from images, but also for various, let's say, sim to real randomization techniques. But this actually idea was much more interesting. We were able to use not only these specific, let's say, structures for action spaces, but we could also learn these action spaces. And once we learned these action spaces, we were able to show that these learned action spaces could directly be used for, let's say, shared autonomy or assistive teleoperation, in which case you are learning an action space and then mapping high dimensional outputs to some low dimensional space. And why is this useful? When intuitively the low dimensional latent space captures the dimensions of variability that you need for the task. So exploration, for instance, only needs to happen in those dimensions. So you only need to do control in the intrinsic dimension of the task. And the same idea, by the way, also worked for legged robots, not only limited to manipulation. So we found that picking better action spaces resulted in both faster learning and easier transfer to real robots. Right. So what I just showed you is a picture of reinforcement learning. I gave you an example of causal data augmentation, but I also argued that we're leaving a lot of structure on the table through model architecture, value functions, learned state, and action encoders. But if we really think about this, this is still single task problems in RL. A lot of the practical problems we are interested in robotics are often compositional, multitask, multi-step. How do we talk about that? Well, one could argue to understand and specify tasks in that space, we also need structure, right? Even if you're doing some sort of imitation learning, one could argue that looking at data and just imitating, well, motions may not be sufficient. In fact, imitating sequences of skills may not be sufficient. The right thing to do is to understand the objectives. And once we can understand the semantic purpose, we can then solve the problem for ourselves with probably a different morphology. So this led us to actually thinking about a model of two-stage solutions, which we have employed multiple times. And I'm going to give you a very specific example of what we found. So the argument is that to understand the purpose of these, purpose of, let's say, the demonstrator or the intent, we need to ground a lot of the actions from the demonstrator. What do I mean by grounding? What I mean by grounding is when we observe, let's say, an entity opening a door, I need to understand the concept of opening a door or opening a jar, and then be able to create a generative model for the scene, which can take in high-level instructions and create estimates of what would the scene be like after application of these actions. And notice these actions are semantic actions. So we are essentially building a causal generative model which is object-centric. So now the pipeline results in a two-stage framework where you have one, a generative model, which is object-centric, a state-to-state prediction model. And you use that generative output to condition a goal condition reactive controller. It can be a policy or an optimal controller. Let's say opening an oven. And then you can solve for opening the oven problem with different agents online. That would allow us to capture general information in our object-centric generative model without sort of overfitting to a particular robot, and then use this information as prior on, let's say, policy learning or even optimal controllers online. So just to give you an example, we have worked on this problem of semantically conditioned video prediction. So this time around, you're given sequences of actions and you're required to predict long-term videos for the effect of these actions. The interesting thing that is different from simple action prediction is that we are not looking for just, let's say, frame to frame level prediction, but we are interested in consistency across time for event level prediction. And we were able to now show that in both simulated and realistic environments, we can learn the context correctly using language guided actions. But the test of this generative model is really to see if you can start from the same state, but provide different set of instructions to see what would happen if that were the case without actually observing that data point. So that would be counterfactual predictions, because that allows you to test your generative model with new sets of actions. And of course, we also evaluated on out of distribution testing, which basically means that there can be entities or sets of actions that have never been shown during training, but are only evaluated during inference. Now, let's assume that you have a mechanism that can specify these goals to you. How would you then solve the problem? So we've also looked at the problem of goal conditioned reactive controllers. In this case, one could argue that you're given some object-centric planner, which can tell you, for example, based on visual input, what would an opened, let's say, dishwasher and oven look like in a pure object sense. But now we need to use that information in an action-centric planner, so which will be a subset of the possible solutions. And then only a subset of those possible solutions are viable for an optimal controller to find. So I'm going to jump through this because we might be running out of time and I don't want to be standing between you and lunch. But I'm going to show you this. In this case, we are able to put this on the real robot where we're not using the model of these articulated objects explicitly. We are only providing direct visual input. The visual processor converts them into point clouds and then predicts what the state of, let's say, an opened dishwasher or an opened articulated mechanism will be, and then tracks the point of the handle and then solves the whole body controller to achieve this task. And because we are using online whole body control, you can actually be efficient and I am sorry for the video not playing. Just give me 1 second. Well, in any case, my computer sort of has stopped cooperating. In any case, what I wanted to show you was that we were able to show that you can build in these systems and use these priors to do online planning with real robots in the real environments. This allows us to not only show that we can do more interesting and more complicated tasks, but also generalize across robot platforms in doing so. So if there is only one thing that you take away from this talk, the way we have been doing reinforcement learning in robotics has often been very naive in using reinforcement learning. However, we are losing a lot of, or we are leaving a lot of structure and juice on the table by not using particular kinds of structure that would be useful for sequential decision making in embodied setups, particularly in robotics. And there's a lot to be discovered in that space. With that, I think I would open the floor to questions. And I would like to thank you all for the privilege of your time. Thanks a lot.
Thank you, Animesh. Okay, do we have a question from the audience here? 9. Maybe Animesh, with the establishing the causal structure and the counterfactual reasoning, that's actually super interesting. And I was wondering, I assume you're familiar with that causal hierarchy from Jadea Pearl, right? So where do you see that do operator go in here? Because that's actually cool, because robots can, operate in the world and interact with the world and thereby establish causality by doing something, which normally, if you just look at statistics, you can't really do anything. In that hierarchy, there's this do operator. So are you formalizing your work in terms of this hierarchy?
Yes, so causal discovery can be done in a variety of different ways. A lot of the causal discovery literature primarily has looked at what you would call non-time series data. A lot of that data comes from different domains. Causal discovery in time series is, in a sense, both easier because it's temporal, but also harder because it's long-term and data can often be higher dimensional. That said, the mechanism of using discovery and evaluating, have you learned an actual causal model, it can be in multiple ways. And the hierarchy that I presume you're talking about from Judea Pearl is one of the mechanisms, of course, to evaluate, let's say, through independence testings of the causal model you have discovered. Essentially, the object of interest after causal discovery is often some sort of directed graph over a set of variables. And the problem that we have, particularly in robotics, is often those variables are not given to us. And then the question that follows after that is, are we interested in only the directional relationships, or are we also interested in explicit mechanisms? So are we interested in what is called structured causal models, SCMs, or are we interested in structured equation models, which are SEMs, which we are related not only in the directed relationships, let's say friction affects speed or something, but explicitly how does friction affect speed, and so on and so forth. So we are looking at both of those things. At times, of course, using independence testing arguments from the literature in causality. Yes.
Yeah, that's very interesting. I think that's one of those fields that's a bit utilized in robotics, causality. That's fair to see. All right, thank you very much for your talk. Maybe in the interest of time, there's one question. Yeah, I might just close the session. You might still ask the question. That's okay.
Absolutely.
Thank you again, Animesh.